Hello viewers, welcome to TG Chemistry. Today I will talk about pericyclic reactions. These are very important topic in organic chemistry for IIT-JAM, GATE, CSIR-NET exams and also for conventional BSc and MSc organic chemistry exam papers. Today I will focus on cycloaddition reactions and will cover the Diels-Alder reaction mainly. And this will be the first lecture of a lecture series where I will cover the pericyclic reaction as a whole. So first let's see about some important points on pericyclic reactions. In a sentence, if we want to say that the pericyclic reaction involves a cyclic redistribution of bonding electrons through a concerted process where mostly it don't involves intermediates, that is without intermediates. But if we want to elaborately express the pericyclic reaction and learn about their important characteristic features, then we have to say that these chemical reactions particularly differ from the ionic and free radical reactions, which are very common in usual organic synthesis purpose in a number of aspects. And this pericyclic reaction has been recognized and extensively studied for very long years. And among the typical characteristics that shared by these type of reactions, some of them involves like firstly, if I have to mention that, I would say that these are relatively unaffected by the solvent changes and in presence of the radical initiator or scavenger reagents or by some other electrophilic or nucleophilic catalysts. So these are not affected by those reaction conditions. So definitely that gives an upper hand when you want to synthesize some complex molecules in presence of varying harsh conditions and also in the presence of several functional groups. Secondly, these reactions proceed by a simultaneous, or we can say concerted, series of bond breaking and bond making events in a single kinetic step. And in most cases, they proceed with very high stereospecificity. This is a very fascinating fact about the pericyclic reactions. I will come into details for this. And in addition to my first 2 points, definitely no ionic or free radical or other intermediates are formed in most of the cases during the reaction pathway for such reaction. Okay, so since the pericyclic reactions are simultaneous reorganization of bonding electron pairs by the way of cyclic transition mechanism, so that's why they have been called as the pericyclic reactions. Okay, so now I will talk about the most common 5 points or types or classes of pericyclic reaction that have been extensively studied. First, as you can see, is if I can have the highlighter. First, you see the cycloaddition reaction over here, and then we can say that electrocyclic reaction, sigmatropic reaction, group transfer reactions, and cheletropic reactions. So these covers mainly, and or rather say these falls in the type of pericyclic reactions. Okay, so today I will cover, or I will talk about the cycloaddition reactions mainly, and within the cycloaddition domain I will talk about the Diels-Alder reaction. Okay, so talking about the cycloaddition reaction, we can say that this reaction results in the formation of the new ring. Definitely we can understand that there will be formation of new rings, and mainly this is designated as A plus B, where A and B refers to number of atoms containing the pi electrons. And cycloaddition reactions are concerted combination of 2 pi electron systems to form a ring of atoms having 2 new sigma bonds. Mind it, they form 2 new sigma bonds and 2 fewer pi bonds, and is called as cycloaddition reactions. And the number of participating pi electrons in cycloaddition reaction in each component is given in the bracket as mentioned over here in A plus B, preceding the name and the reorganization of the electron, and it can be in most of the cases depicted in curved arrows. Okay, and for representing the movement of the pair of electrons. Okay, and this in these cycloaddition reactions, the three important classification of the cycloaddition reactions are, as you can see over here. That first comes the Diels-Alder reaction, the most studied reaction, cycloaddition reactions in pericyclic reaction, and then comes the 1,3 dipolar cycloaddition reaction, and then 2+2 cycloaddition reaction. Talking about the Diels-Alder reaction, in organic chemistry, the Diels-Alder reaction is a chemical reaction usually which occurs between a conjugated diene and a substituted olefin, which is most commonly termed as the dienophile, and they form a substituted cyclohexane derivative in most of the cases. Now, this prototype of pericyclic reaction is a genuine example of concerted mechanism. Okay, and more specifically, if we want to say that it is classified as the thermally allowed cycloaddition reactions, but in the parenthesis we can say the pi electron systems like 4+2 cycloaddition reaction, 2+2 cycloaddition reaction, like this. And it was first discovered by Professor Otto Diels and his student Kurt Alder in 1928, and both of them received the Nobel Prize in 1950 for their discovery. And in Diels-Alder reaction, it's as I said, between the conjugated diene and dienophile, and the highly effective method, this one is a very highly effective method for the formation of cyclohexene rings. Okay, here you can see the general representation of the Diels-Alder reaction, where a diene reacts with a dienophile. Now we have, before I move further, I would like to say that we have heard about the electrophile and the nucleophile, and in those cases we can see their affection towards nucleus or electron. Okay, so phile means loving, we know that. So in that case, dienophile means a olefinic pi system which loves to react with the diene. So these are dienophiles. Now the dienophiles can be of open chain, open ring, or cyclic type. I will come into details when I will talk about different dienophiles and their preparation of the dienophiles as well, and dienes as well. So this is a classical representation of the Diels-Alder reaction, where the diene, which is of 4 pi system, reacts with the dienophile, which is of 2 pi system, to form a cyclohexene derivative, and as I said before, the formation of 2 new sigma bonds, which are shown by the red color here. Okay, so this is a general representation. In Diels-Alder reaction, we will mainly study here the normal 4+2 Diels-Alder reaction, inverse electron demand 4+2 Diels-Alder reaction, and also hetero 4+2 Diels-Alder reaction. And I will talk in details of each time in lectures when I will talk about them. Okay, so today we will focus mainly about the normal 4+2 Diels-Alder reaction, in which the diene is electron rich and the dienophile is supposed to be electron poor. Okay, whereas in case of inverse electron demand 4+2 cycloaddition reaction, the reverse will be there. As you can see, this is the inverse process. So in that case, the diene should be electron poor and the dienophile should be electron rich. And in case of hetero Diels-Alder reaction or hetero 4+2 cycloaddition reaction, the dienophile system can have, or the diene system can have, the hetero atom containing functional groups like carbonyl or imine, and in that case they form inherently, or by default they form heterocycles as the product. So these are known as hetero 4+2 cycloaddition reaction or hetero Diels-Alder reaction. Now we will talk about the requirements of the diene. Dienes can be open chain or cyclic substrates. So this can be both, but the most important thing is that the diene should be electron rich and the reactivity should be enhanced by electron donating group as substituents in the diene system. Now in case of the diene, the open chain dienes, I mean in case of closed chain diene, there are limitations in the conformational orientation or conformational changes, whereas in case of open chain diene, it can acquire 2 conformations. like this one, which is generally known as the S-cis diene. The other one where the diene system is in the trans position and known as S-trans dienes. So for Diels-Alder reaction, most reactive diene system has to be the S-cis diene. So when the diene system will be in the S-cis conformation, that will be more reactive towards or highly reactive towards Diels-Alder reaction. Whereas if the diene system is S-trans, then this will be quite unreactive for the Diels-Alder reaction. Okay, and so in that case, S-cis means two double bonds are cis to each other, and S-trans where the two double bonds are trans to each other. So these are very important points that we need to analyze whether a Diels-Alder reaction will proceed or not. I mean, you cannot look for the diene system only, but you also has to look for the right reactive conformation of the diene, which is basically S-cis. Next, I will show some dienes, cyclic dienes, and with S-cis conformation and S-trans conformation, S-trans conformation. Here you can see the diene has to adopt the S-cis conformation for the reactivity, and here these are in the these are example of cyclic diene. However, you can see all the diene systems are in the S-cis form. Okay, even in the exocyclic diene as well. Whereas the cyclic diene which are permanently is in S-trans conformation, they are unreactive to the Diels-Alder reaction, and so in that case, this is another example for that, where you can see this diene system, this is of S-trans, and all these three diene examples are S-trans dienes. So these are not reactive towards the Diels-Alder reaction, or rather say these are unreactive to that. So the general stereo requirement for the diene that it has to adopt the S-cis conformation to be reactive. Okay. Next comes some useful preparation regarding the dienes. Okay, how the dienes can be obtained. In most cases, it can be given to you when you have to go for a reaction with the diene and dienophile. It can be given to you. In some cases, if the question is a little bit tricky, in that cases you should be provided with a precursor from where a diene will be formed, and then it can react with a dienophile to produce the cyclic product. Okay, so here couple of first examples you can see from the cyclohexanone derivative with triflic anhydride in presence of pyridine. You can have this cyclic triplet enolate, which further upon Heck reaction or Heck coupling in presence of palladium acetate and some vinyl halides or vinyl groups in presence of that can form a diene system, which is basically the S-cis diene. As you can see, this is a S-cis conformation. Okay, in the another case where by means of enine metathesis, where Grubbs 2 second generation catalyst can be used to form the enine. Here you can see this is the this is the ine system, so this is an enine system, and this undergoes readily the enine metathesis reaction in presence of Grubbs catalyst to form such a product, a cyclic conformer, where you can find the S-cis diene system. So these are very useful diene systems, and these are the precursor for the formation of diene. I have three more examples here you can see. Yeah, so here you can see the enone system, which is this enone system you can see over here, which transformed by means of Shapiro reaction in presence of tosyl hydrazine and methyl lithium by a cyclic diene system, and this is also S-cis diene. When an alpha beta unsaturated ketone acyclic system having a methyl group over here adjacent to the carbonyl group in presence of base and TMS chloride, that can form eventually a S-cis diene system, which will be useful for the Diels-Alder reaction. The allylic alcohols, substituted allylic alcohols, also by means of dehydration reaction, they can form the S-cis diene system, and these allylic alcohols, they can be formed by means of reaction with vinyl magnesium bromide when react with the acetone in acidic condition. Then they can form the allylic alcohols, and by dehydration you can have these Diene systems. So these are some examples for synthesizing some useful Dienes. Okay. So next, the electronic requirements of the Dienophile. So we have seen the regarding the Diene, the stereo requirement of the Diene, and electronic requirement of the Diene, and their synthesis. Now we have moved towards the electronic requirements of the Dienophile. Here the Dienophile can be open chain or cyclic as well, and in that case you can see, but the important point is that the Dienophile should be electron deficient and reactivity enhanced by the electron withdrawing substituents in case of Dienophile. Okay, so it has to attract the Diene towards itself. So in that case, in case of the open chain Diene systems, which are shown over here, in most of the cases you see some electron withdrawing groups or heteroatoms are attached with the olefin system, thereby making the Dienophiles electron deficient. And also you can see some cyclic Dienophiles here also. So this is the Dienophile system, the anhydride with the Dienophile system, and this is an alkyne which can be used as the Dienophile as well. So these are few representative examples of Dienophiles where you can really easily understand or realize the electronic requirement, which are very important for a Dienophile to give a better yield in the Diels-Alder reaction. So, and they can be of cyclic and open chain both. Here are the examples. Next comes the preparation of some Dienophiles. Like the Dienes, we will see the preparation of some Dienophiles as well. Where the nitromethane, you can see in presence of formaldehyde and H2SO4 can react or can produce the Dienophile, the vinyl nitro compound here, which can act as a Dienophile. And also from this 1,4-dihydroxybenzene by means of potassium KBrO3 in presence of acidic media, it can form a Dienophile system in either way. I mean, this one can react with as the Dienophile, or this one. Both of them are eligible for reacting in the Diels-Alder reaction as Dienophiles, and they can react with two Diene in either side. Okay, so this is another example. Then we can go for another reaction. In the manic reaction, you can see with the cyclic ketone when react with the formaldehyde, and by means of acidic media in manic reaction, you know the protocol of manic reaction, you eventually can lead to the formation of a Dienophile system, this one, which is an exocyclic olefin basically of a cyclic ketone. Here also this is another with vinyl nitrile. From here you can have the different Dienophiles containing the ester functional group or amide functional group, depending on the requirement of reaction when we are intend to synthesize some particularly important class of organic compounds, and that depends on the requirement of the Diene as well. So these are some preparation process of the Dienophiles as we learned. Next comes the stereochemistry of the Diels-Alder reaction. As I said before, that the Diels-Alder reaction is a stereospecific reaction, and the relative stereochemical relationship of the Diene and the Dienophile is reproduced in the product. Okay, and the Diels-Alder reaction occurs due to the overlapping of the p orbitals of the Diene and the Dienophile, which lie perpendicular to the plane of the carbon atoms. So this is a requirement, or this is a process by which the Diels-Alder reaction proceeds. Hence, we can say that the Diene possesses two faces, namely the top face and the bottom face, and the Dienophile can approach either side from top face or the bottom face, and lead to the formation of a racemic mixture in those cases. Okay, so these are general process for the mechanism. I will come into detail of the stereochemistry of the Diels-Alder reaction in the next slide. But before we move further, we need to understand the frontier molecular orbital approach, where three terms are very important. First is the FMO, which is the abbreviation of frontier molecular orbital. Then the term is HOMO, the highest occupied molecular orbitals, and LUMO, which represents the lowest unoccupied molecular orbitals. And the FMO theory is the occupied orbitals of different molecules, they used to repel each other. Okay, whereas the occupied orbital of one molecule and the unoccupied orbital of other molecule, that means the HOMO of one molecule and LUMO of another molecule, they interact with each other, causing the attraction. Okay, so this is the attraction kind of interaction. So in that sense, the FMO simplifies the reactivity by the interaction between the HOMO of one component, I mean that can be from the diene or dienophile, and the LUMO of the other component, which can be of the diene and dienophile as well. So first here we will talk about the FMO approach, where we consider the MO of the, that means molecular orbital of the diene. Here we will take the 1,3-butadiene system as a representative diene, which usually we find in all the classical textbooks, and ethylene molecule as a typical dienophile. So both are unsubstituted ones, and the ground one actually. So let's see. So this is the molecular orbital diagram for the diene, which is 1,3-butadiene, and dienophile, which is basically ethylene. Here you can see the in case of the diene, in the MO picture you can see it will have the molecular orbitals Chi1, Chi2, Chi3 star, Chi4 star, and where Chi2 will be the HOMO for the diene and Chi3 star should be the LUMO for the diene. And for the dienophile system, it should be pi and pi star only, where this pi1, that the pi should be the HOMO, and the pi star, this is the LUMO for the dienophile system or the ethylene system. Now here is a representation of, under thermal condition, how electronic configuration or distribution takes place in the molecular orbitals. So we can understand that the 4 pi electrons in the diene system can be first distributed in Chi1 and Chi2, and that's why this is the highest occupied molecular orbital Chi2 for the butadiene system. And Chi3 star, this is the lowest unoccupied one in case of thermal condition. Whereas in case of photochemical condition, the electron from HOMO can move to the Chi3 star. So this should be the photochemical condition, this should be the electronic distribution for the diene system. And in case of dienophile, the 2 pi electrons can be in the pi orbital, the HOMO orbital only, you can see over here. Whereas in case under the photochemical reaction condition, they can move up to the LUMO or pi star orbital. So this will be the electronic configuration during the photochemical reaction conditions for the dienophiles. So these are very important to understand, because when you are considering the thermal condition or photochemical condition, you need to keep in mind the electronic distribution in the MO of the diene and the dienophile. That can help you to predict the products. Okay. So as I said before, that I will talk about the stereochemistry of the Diels-Alder reaction, and as I mentioned about the top phase and the bottom phase, which are two possible ways or options for a diene to have, and the stereochemistry of both the diene and dienophile are retained in the product in most of the cases. Okay, and the reaction controls the relative stereochemistry of the 4 contiguous center, which involves, or which actually involves 2 from the diene and 2 from the dienophile. Okay, so here we will see the interactions and we will see how the product is formed. For example, you can consider the diene over here, where the top phase and the bottom phase, you can see, if we can look from the top phase, this is this one, and this is the bottom phase approach. And in case the dienophile approaches from the bottom phase, and what should be the product in that case? So we will have the cyclohexene derivative, and which will have the stereochemistry of respective all the 4 carbons here. And as these are only hydrogen atoms and simplest system, so in that case not much difference. But when we will have the substitution here, we can definitely we have to assign the stereochemistry of the functional groups around these 4 carbon centers, and or rather depending on the carbon centers of the products. So stereochemistry of Diels-Alder reaction is a very important point to understand. Okay. Then comes the stereochemistry of the Diene system. This is a very significant slide where you need to understand the rule of thumb, that the given the bottom phase approach of the Dienophile, as you see in the previous slide, that the inside substituents of the Diene will eventually become the beta configuration in the product, and the outside substituents of the Diene will become the alpha configuration in the product here. So here it is a representative Diene system where you can see these are the outside substituents, that is these methyl groups here, and inside substituents are these two hydrogen atoms which is shown over here. These are the inside substituents. So this is in case of Diene. Now, as I said, the thumb rule said the inside substituents of the Diene will become the beta configuration. That means they will go the below the plane stereochemistry, rather say, or the cis conformation by themselves eventually. So here you can see those two methyl group goes below the plane over here, and the hydrogen atoms which are inside substituents, they go above the plane. So this is very important to understand the Diene system and their substituents, and how after the reaction in the product their stereochemistry will be. Now, as here the Dienophile is a alkyne system with dimethyl acetylene dicarboxylate, and these two carbon center are sp2 hybridized, so there are not much stereochemistry to assign for these two carbon centers. Okay, so here we can assign the stereochemistry of the respective carbon centers over here. One is here, another one is here, by means of the thumb rule which I mentioned just a bit ago. So using this thumb rule and remembering this, we can define the products in next cases. Here this is also the stereochemistry of Diene and the Dienophile system for the reaction. Here you can see this is the Diene system, and as I said in the thumb rule, if the Dienophile is approaching in the bottom phase approach, then the outside substituents will go in the beta orientation or beta configuration, whereas the inside substituents will acquire or will adopt the alpha configuration in the product. So here, if you can assume that this Dienophile can approach, this Dienophile approaches to the Diene in the, from the bottom phase like here. So these two methyl groups, as you can see here, these are the outside substituents. So eventually in the product, this has to go below the plane. Let's see here in the product, you see these two methyl groups are below the plane. That means they have adopted the beta configuration. Whereas the two inside substituents, these are hydrogen atoms, they adopt the alpha configuration. And from the chair conformation, you need to draw the chair conformation to better understand the orientation of the substituents and how you can assign them when you write down in a cyclic way apart from the chair conformation. Okay, so this, I hope you understand this point. And here the stereochemistry of the Dienophile, this is also very important. And given the bottom phase approach of the Dienophile, substituents on the Dienophile can take two different orientation with respect to the plane of the Diene, and they can be called as endo and exo. So if we consider the bottom phase approach, it can be in either way. So we consider the Diene system here like this Diene system, and we consider the Dienophile with this vinyl formyl group containing Dienophile. And if the Dienophile approaches at the from the bottom phase with this orientation, this is known as the endo orientation, or the endo configuration of the Dienophile while approaching the Diene from the bottom phase. And this is the exo approach, where the Dienophile is oriented in such a way. Okay, so in terms of orbitals, we can understand that when we write down the four conjunction, this carbon center, these two from the Diene, these two from the Dienophile, when they approach from the bottom phase, the substituent is inside. This one is the endo approach, and here the similar approach, but the substituent of the Dienophile is away from the vinyl double bonds. That means this represents the exo approach. Okay, so I will come into detail next slide. Here you can see this is the representative example, and where we can understand the stereochemistry of the Dienophile, where it represents the endo approach. And in that case as well, this is the orientation of the dienophile. As you can see, this is the endo orientation when we consider the bottom face approach of the dienophile to the diene system, and then from there on, by means of the interactions, and if you need to write down or form the chair conformation to better understand the orientation or the stereochemistry of the carbon centers, and from there on you can understand that the two outside substituents here, the phenyl groups of the diene system, will adopt the beta orientation, that is the below the plane geometry over here. And for the endo approach, definitively the formyl group will be the below the plane stereochemistry as well. Next, we will see the exo approach of the similar kind of reaction, where we realize that in that case also, here you see in the product quite similar way, as the two phenyl groups over here are the outside substituents and the dienophile is approaching from the bottom face. So in that case, you can also find in the product that two phenyl groups have adopted the beta configuration and they are below the plane in the product. The 1,4 relationship obviously, and in the below the plane. Whereas the formyl group, the stereochemistry of the formyl group, this adopted the above the plane stereochemistry, as evident from this chair conformation over here. You can understand with the plane of the chair, this is above the plane, getting the equatorial conformation or the orientation rather say. So that should be above the plane stereochemistry for the formyl group. So this is the stereochemistry of diene and dienophile, and the approaches exo and endo approach when we consider. Next comes the Alder's endo rule, which is very important to understand the orbital overlaps and the additional interactions associated with them. In that case, the endo mode of addition is usually preferred to the exo addition due to the secondary orbital overlap between the dienophiles activating substituent and the diene. So this is very much evident from the representation over here. So you can see the diene system over here, and the another diene system or the dienophiles activating substituents, if you can understand that. And then you can see there are additional secondary interaction like this one and this one, which is missing in case of exo orientation. Okay, so this is only the two carbons from the diene and two carbons from the dienophile, only interaction between these two in case of exo orientation, whereas no secondary, that means there is no secondary orbital interaction, and here two more secondary orbital interaction which eventually stabilizes the product, and therefore the secondary orbital overlap in the endo orientation or endo mode of addition rather say gives more stable product. So in that case, this is the Alder's endo rule, that the endo mode of addition usually preferred to the exo addition, while when the dienophiles activating substituents and the diene interact with each other. This is very important to understand. Okay, so the product formation and the stability of exo and endo product. Next comes a very important point, the regiochemistry of the Diels-Alder reaction. And for a monosubstituted diene system, the outcome of the product depends on the carbon atom where it is substituted. If not substituted, then the situation is quite simpler, and it is a bit easier to predict the regiochemistry of the product in the Diels-Alder reaction. And in that case, you need to consider two classical cases, as I mentioned over here, where the electron donating substituent could be present at carbon 1 or carbon 2. Here this is the 1, 2, 3, 4 carbon. You can see for one substituted diene system, the R group is the electron donating substituent here, and R group can be at the 2 positions. So this is only 2 positions are possible here, because this is in the diene system only these 2 orientation or possible substitution can be there. Okay, if we are talking about the mono substitution of the diene system. So 1 substituted diene or 2 substituted diene. Okay, so let's see how it works. So first, the 1 substituted diene system, when it reacts with the dienophile, it mainly gives the 1,2 product. Okay, that means the orientation of the dienophile, which will have eventually the electron withdrawing group. Here R group is electron donating, mind it, and dienophile will have the electron withdrawing group. So in that case of reaction, when we form the cyclohexene derivative, the diene the orientation of the substituents of diene and dienophile will be in 1,2 position. That means we will get the 1,2 product as the major product. But we will not get the other option, the 1,3 product, we will not get that one. Okay, so this is the regiochemical implementation or regiochemical outcome of the Diels-Alder reaction when the diene have electron donating group at one position, and then in that case whatever be the dienophile will be which will have the electron withdrawing group, that the orientation of the dienophile has to be that way, not this one. Okay, so 1,2 product will be formed in that case. So this is the regiochemistry for the Diels-Alder reaction with one substituted diene system. Now we will see the more regiochemical outcome and how these systems works. Okay, the regioselectivity of the preference of the 1,2 product is explained by considering the polarization of the diene and the dienophile to understand that the connection or the bond formation involves an electron rich center of the diene and the electron deficient center of the dienophile. Okay, so here you can easily understand that if you have a electron donating group in the diene, eventually by means of through conjugation you can increase the electron density at that carbon. So that carbon is basically electron rich center. So that carbon will tend to interact with the electron deficient center, and by means of having electron withdrawing group in the dienophile at that position, so it pulls the electron from here and creating the electron deficient center in the dienophile at that carbon, the farthest from the electron withdrawing group. So the general mode of formation of product should be electron rich center must get the electron deficient center to react. So thereby in that case we will have the orientation of the diene and dienophile in such way, and 1,2 product is the major one in that case of one substituted diene system. Okay, now if we consider the 2 substituted diene system, it will eventually end up giving the 1,4 substituted product. Let's see how it happens. Here this is the 2 substituted diene system where this R group is electron donating group and the dienophile eventually will have electron withdrawing group. As I said, this is the normal 4+2 cycloaddition reaction of the Diels-Alder reaction. So in that case the major product is supposed to be this 1,4 addition product or the 1,4 product where the electron withdrawing group of the dienophile and the electron donating group of the diene will be at 1,4 position to each other. We will not get any 1,3 product in that case as well. So in terms of electronic character, let's see. So this we can understand that when you have a electron donating group in the diene, so at the adjacent carbon, because in that case you don't have the privilege of conjugation through conjugation, so in that case the nearby carbon get the electron excess, that is this is the electron rich center, and then to react with the dienophile has to have the electron deficient center which is nearest to the electron rich center. So this should be the orientation for the dienophile. That means the dienophile will always have the terminal carbon as the electron deficient center. So definitely now the deficient center has to bring close towards the electron rich center of the diene, and thereby we will have the 1,4 addition product here. So this is the major product where 1,4 addition product will be the major product in or the regiochemistry should be the 1,4 product for diene and dienophiles. So thank you very much for watching TG Chemistry. Keep watching my channel and please subscribe my channel if you like the videos, and don't forget to press the bell icon to get notifications whenever I upload the videos, and the other videos of this lecture series on pericyclic reactions will be uploaded very soon. Thank you.